The target goal for the athletic shoe analysis is to determine an in-shoe method of measuring forces on a shoe cushioning system when performing moderate to high levels of activity. This will be done using force transducers or sensors placed inside of the shoe to track the forces on the foot during the activity. Another goal for this analysis would be to improve upon existing ASTM shoe testing. Current ASTM tests use static weights or Instron machines to test the cushioning systems on shoes. This is not a direct test of the forces on a user's foot while walking or running, however. Hopefully this test will improve upon that. The purpose of shoe cushioning systems is to reduce the force on a user's foot, which in return results in less force on a person's joints, and particularly the knees. Therefore, this test method could be used by everyday runners to find the ideal cushioning for their current shoe or to find if their current shoe has fatigued over time. Runners experience impact forces due to the ground upwards of 2 to 5 times their body weight with each footfall. Similarly, walking forces can range from 1 to 1.5 times an individual's body weight. The ground reaction force produces vibrations or shock waves due to the heel strike, which are transmitted by the bone of the foot to the rest of the body. The intensity of the shock wave has been linked to the development of running-related injuries. Proper athletic footwear reduces impact forces and shock waves by approximately 33 and 36%. Patellofemoral pain syndrome, also known as runner's knee, is a common ailment among runners. Runner's knee is the pain or discomfort due to the kneecap contacting the femur. This can result from repeated bending of the knee, direct trauma to the knee, or problems with the feet. And as seen in this diagram, the patella rubs up against the femur, causing discomfort or pain. This is actually a common ailment among athletes in general. While this can be a biomechanical problem or a thigh muscle strength issue, this can also be prevented with proper running shoes. A reduced force on the foot will transmit to less overall fatigue on the knees over a long period of running. The plan is to develop a test that utilizes transducers or force sensors to actively measure the force. Not only just measuring one force at a time, it hopefully would measure rapid forces to test the fatigue over impact cycles. So the goal would be to develop a test that was accurate within 10 pounds or better and to record an ideal amount of data per second. My first attempt was making a cantilevered beam concept based on load cell designs for common bathroom scales. Strain gauges would be placed at a deflection point at the base of the cantilevered beam, and when the beam was deflected, it would produce microstrains which could be translated into forces. Using 1018 steel, the dimensions of the beam itself would be a ½ inch long, 1 inch wide, and 0.1875 inches thick. This ensured that the bending strains would be within 100 to 1,000 microstrains from a force range that would be equivalent from walking and running. This range was determined based on my body weight. A design consideration was to elevate the cantilevered beam portion so when placed inside the shoe, it would deflect when stepped upon. However, the problem with this design was the Hackman-Minestrone microcontroller was not able to read and record the microstrains coming from the beam deflection, as well as another problem with the practicality of placing a small steel transducer inside a foot, which was too cumbersome to be practical. My second attempt was a simply supported beam, where the center of the beam would deflect, and the microstrain could be read with strain gauges through the Hackman-Minestrone microcontroller. Simply supported beam would be a modified and smaller iteration of the transducer lab we learned in ME410. This transducer was also made of 1018 steel, and the dimensions of the beam would be 1.5 inches long, 1 inch wide, and 0.1475 inches thick, which would result in bending strains of 100 to 1,000 microstrains, and this would cover the same force range as the last transducer. Unfortunately, similar to the first attempt, this transducer's microstrain was not able to be read on the Hackman-Minestrone microcontroller. Also, the steel, although smaller than the first iteration, was still too cumbersome to place inside of an athletic shoe. Given that strain gauge transducers were not ideal for this application, pressure sensors were researched. I found the FlexiForce pressure sensor, which, although it had a 25-pound maximum limit, could be altered and changed in its circuitry to allow for a range from 0 to 1,000 pounds. This was using an op-amp circuit which would reduce the drive voltage or resistance to the feedback resistor, as seen in this diagram. Unfortunately, the voltage levels were too small to be outputted as an analog number from the Arduino Uno code I had set up. The analog output saw no change with the change in the resistance of the pressure sensor when it experienced force. Fourth time being a charm, I finally found a way to get it to work. I still utilized the same FlexiForce pressure sensor from my third attempt, but I altered the circuit to output the proper voltage. In order to increase the pressure sensor's range, a voltage divider was made to reduce the output voltage to work with the Arduino Uno. The step accurately returned force measurements that ranged from 40 to 180 pounds. This is not ideal for all people, but it was acceptable for my personal body weight only during walking, however. So all of my tests would have to be conducted while walking. So my test setup included an Arduino Uno and its accommodating software, a FlexiForce pressure sensor, breadboard, a 10 kiloohm resistors, 22 gauge wire, and in this case ASICS Gel Phoenix 2, which were just running shoes that I personally use. I performed a weighted calibration of the sensor itself in order to find the corresponding force to the Arduino analog output. The result was fairly linear, with an R-squared value which was acceptable at 0.97. So my test plan could be broken down into 4 separate tests. First one was walking barefoot with the sensor on the heel. Second one was walking with the shoe on with the sensor on the heel. The third one was walking barefoot with the sensor on the ball of my foot. And the fourth one was walking with the shoe on with the sensor on the ball of my foot as well. The test would be walking 30 feet on flat concrete, and each test would be conducted 3 times. I would find the average peak force from each step. So here's my test setup. I have my force sensor inside of my shoe attached to my heel. It's all hooked up to my voltage divider circuit on my breadboard, which is hooked up to the Arduino Uno. This Arduino Uno has been coded to give me an output which I can record and take the data from. My first test was with the force sensor placed on the heel of my foot. It was securely held in place with tape. And yes, while the force sensor is sensitive to temperature changes, it was tested to be accurate within a change of 5 pounds, which was within the 10-pound accuracy range that was my target goal. So here's my test. Conducting this test while barefoot, and I'm walking 30 feet. This would give me a standard of about 5 steps per test. This test was conducted 3 times, and I collected and recorded the data. In general, each step was consistent, and each trial had roughly the same walking cadence, which suggests identical loading and unloading on my heel for each step. The cycle for every step is roughly a second, so therefore a sampling time of 40 data points a second is more than adequate as a sampling rate. As predicted with the journal article titled Ground Reaction Forces at Different Speeds of Human Walking and Running, my walking steps were within 1 to 1.5 times my body weight. These peak forces from each step in all 3 trials were collected and averaged together to find an average peak force. This will be mentioned later. So the same test was duplicated and all 3 tests were performed, but in this case it was with shoes on. So my heel still has the force sensor attached to it, but I'm wearing shoes. This data was recorded and collected. Once again, the data was very consistent and each trial had roughly the same walking cadence, so that loading and unloading should be more similar to each other. If you compare this data to the first set of data, there is less amount of force, which will be averaged out and mentioned later. So for my second half of testing, I simply moved this force sensor to the ball of my foot to a location where it would predictably have the highest range of forces. So once again I conducted the barefoot test 3 times, but I will spare you from showing the video twice. So once again it looks like we have good data with a good walking cadence that will have consistent results in every trial. The force peaks out to around 140 and the averages will once again be calculated for later. The final test was conducted with my shoe on and the force sensor is still on the ball of my foot. It was conducted 3 times. Once again, all 3 trials seem to have similar walking cadences and would be averaged out for later. The forces seem to peak out around 130, 120 in that range. So in every test, each trial was averaged together to find a peak force as well as the percentage of body weight. So for the barefoot heel test, it was approximately 158 pounds of peak force. For the shoe heel, it was 125. For the barefoot ball of my foot, 135. Shoe ball of my foot, 112.8. So as a percentage of my body weight, which is 130 pounds, the barefoot heel was approximately 121%, shoe heel 96%, barefoot ball 103.9%, shoe ball of my foot 86.8%. So if you take this data and you compare it to the literature value, you see that the tested value for the heel force reduction with the shoe on is a 20.8% reduction in force. For the ball of my foot force reduction with the shoe, it's a 16.5% reduction. So the literature value claims that a proper running shoe will be approximately a 33 to 36% decrease in force. The reason for the differences between the literature and my test values may have been different due to a variety of variables. One being that I used one set of athletic shoes. Perhaps it would have been different if I used a variety of athletic shoes, but I was constrained by my project budget. Two, it could have been the fact that I only had a walking test compared to a running test. I was constrained by my equipment, but this could have been an issue. And three, I used my personal athletic shoes, which probably fatigued over time. They are several years old, and perhaps the EVA foam or the rubber outsole may have fatigued, and it's not providing the same cushioning response. So in the end, I was successful in creating a test that allowed for instantaneous force data to be collected while the shoe was in use, as opposed to ASTM tests. And another advantage for this test would be its potential use by athletes to know when a shoe is fatigued and no longer provides the adequate cushioning that they desire. If I have any recommendations for future tests, it would be to test more shoes and more varieties of shoes, preferably new ones so they're not fatigued over time. Another recommendation I have would be to use other force sensors that could measure adequate force ranges for running tests. And as you may have seen in the video, I had trouble carrying my computer as well as my Arduino and circuit while I was conducting the test. So a wireless equipment would be much more beneficial for future tests. So that concludes my presentation for my athletic shoe analysis project. Thanks for watching.